When we visualize the battlefields of the ancient Mediterranean, our minds default to the visceral clash of bronze and iron. We imagine the chaotic crush of infantry, the phalanx, the legion, and the sweat-drenched exhaustion of hand-to-hand combat. Warfare in antiquity is almost universally understood as fundamentally manual labor, limited entirely by the physical endurance of the human body. But hidden within the arsenals of the Hellenistic kingdoms, and later the Roman Empire, was a terrifying mechanical anomaly. It was a weapon that defied the era's reliance on human stamina and foreshadowed the industrial slaughter of the 20th century. This was the Polybolos, a repeating catapult that effectively functioned as the world's first machine gun, built over 2 millennia ago. To understand how such an anachronistic piece of technology existed in the ancient world, we must first discard the popular myth that ancient engineering was primitive, heavily reliant on simple leverage or brute force. The engineers of Alexandria and Rhodes were not merely builders of static walls, they were pioneers of complex kinematics. They understood gear ratios, pneumatic resistance, and cyclical motion. The Polybolos was not a magical prototype or a theoretical sketch in a philosopher's notebook. It was a highly pragmatic, ruthlessly efficient weapon of war, designed to solve a specific tactical problem, the agonizingly slow rate of fire of standard siege artillery. In a typical Scorpion or ballista, a highly trained artillery crew had to manually draw back the heavy torsion springs, lock the catch, place the bolt, aim, and fire. This multi-step process meant that even the best crews could only unleash a handful of projectiles per minute. During a chaotic siege or a rapid naval boarding action, those seconds of reloading were moments of critical vulnerability. The enemy could rush the artillery positions, or the psychological shock of the bombardment would dissipate. The military institutions of the Hellenistic world, funded by the massive treasuries of the Ptolemaic kings, demanded a solution. They demanded a machine that could lay down continuous suppressive fire without pausing for human reloading. They wanted to automate the sequence of death. The answer came from an engineer named Dionysius of Alexandria, who approached the problem not by making the weapon larger, but by completely reimagining the mechanics of ammunition delivery. He realized that to achieve a high rate of fire, he had to eliminate the discrete, individual actions of the artillerymen and combine them into a single, continuous, fluid motion. The result was an astonishing piece of military hardware that removed the human element from the loading process entirely. The mechanical genius of the Polybolos lay in 2 revolutionary mechanisms that would not be seen again in a military context until the Gatling gun of the 19th century, the gravity-fed magazine, and the flat-link chain drive. To automate the firing cycle, Dionysius had to design a system where a single action from the operator could cock the weapon, drop a new bolt into the firing groove, and release the trigger, all in a continuous loop. The operator stood behind the weapon and simply turned a large wooden windlass back and forth. But how did a simple rotary motion translate into the complex sequence of loading and firing? The secret was a drive chain made of iron flat links, incredibly similar to a modern bicycle chain. This chain ran along the length of the weapon's stock, looping around pentagonal gears at the front and the rear. When the artillerymen turned the windlass, the pentagonal gears rotated, pulling the heavy iron chain backward. Attached to this chain was the cocking slider. As the chain moved backward, the slider was dragged with it, catching the bowstring and pulling it back against the immense tension of the twisted animal's sinew springs. This solved the problem of cocking the weapon, but the true innovation was the ammunition feed. Mounted directly above the firing groove was a wooden hopper, a gravity-fed magazine containing a stack of heavy, iron-tipped bolts. In a standard catapult, a soldier had to manually place a bolt into the groove, risking his fingers and wasting precious time. In the Polybolos, the movement of the slider itself automated this action. The wooden block that held the bowstring featured a carefully carved, cam-operated rotating cylinder. As the slider was pulled backward by the chain, it cleared the space beneath the magazine. Gravity then forced a single bolt to drop from the hopper directly into the firing groove. It was a beautifully elegant, institutional solution to a complex mechanical problem. The moment the bolt fell into place, the slider hit a precisely angled trigger mechanism at the back of the stock. The trigger engaged, the catch released, and the torsion springs violently snapped forward, launching the bolt with lethal velocity. The operator then reversed the motion of the windlass, sending the slider back to the front of the weapon to catch the string again. Turn the crank back, cock the weapon, load the bolt, fire, turn it forward, reset. The cycle could be repeated as fast as the operator could physically rotate the windlass. A single, relatively untrained soldier could lay down a continuous hail of armor-piercing projectiles, creating a localized kill zone that no enemy infantry could hope to cross. The machine gun had been born. However, the practical reality of fielding the Polybolos on a continental scale revealed a fundamental limitation of ancient logistics. If this weapon was truly capable of such devastating automated firepower, why did it not conquer the known world? Why didn't every Roman legion field batteries of repeating ballistae to mow down their enemies? The answer lies in the ruthless, uncompromising demands of industrial standardization. For the gravity-fed magazine of the Polybolos to function properly, every single bolt placed into the hopper had to be perfectly uniform. If a wooden shaft was even a fraction of a millimeter too thick, it would jam in the magazine chute. If it was slightly too long, it would not drop into the groove. If the iron arrowhead was too wide, it would snag on the wooden casing. In the 19th and 20th centuries, the invention of the metallic cartridge and precision machine tooling allowed for the mass production of identical ammunition, making the Maxim and Gatling guns viable. But in the ancient world, ammunition was manufactured entirely by hand. Blacksmiths hammered out iron heads one by one, and carpenters shaved down wooden shafts using hand planes. While Roman and Hellenistic military workshops, the fabricae, were capable of impressive mass production, achieving the micromillimeter tolerances required for an automated magazine feed was nearly impossible to sustain under wartime conditions. In the sterile, well-funded workshops of Alexandria, a master carpenter could craft 50 perfectly identical bolts for a theoretical demonstration. But in the muddy, rain-soaked reality of a siege camp in Gaul or a frontier fort in Syria, wood warps. Moisture swells the shafts. Iron rusts. A single warped bolt out of a batch of 20 would catastrophically jam the entire weapon. Clearing a jam in a highly tensioned torsion engine while under enemy fire was a terrifying and dangerous prospect. The institutional function of artillery in the ancient world prioritized reliability over an extreme rate of fire. A standard, single-shot Scorpion ballista was much slower, but it was almost immune to minor ammunition variations. If a bolt was slightly misshapen, the artillerymen could simply force it into the groove by hand. The standard engine forgave the imperfections of the supply chain. The Polybolos did not. It was a machine that required a level of logistical perfection that the agricultural economies of antiquity simply could not guarantee. The weapon was a brilliant piece of mechanical engineering that ultimately outpaced the manufacturing capabilities of its own era. It was a paradox, a machine gun forced to rely on handmade bullets. Beyond the staggering logistical hurdles of ammunition standardization, the Polybolos also faced a significant tactical drawback regarding its targeting mechanics. Because the operator had to stand directly behind the weapon and vigorously crank a heavy wooden windlass back and forth, it was nearly impossible to smoothly track a moving target. The sheer physical effort required to overcome the massive torsion springs caused the entire wooden frame of the machine to violently shake and vibrate. While a modern machine gun can be smoothly swiveled on a tripod to sweep across an advancing enemy line, the Polybolos was essentially locked into a single, highly concentrated firing vector. It was not a weapon for dynamic, fluid infantry battles. Instead, its primary institutional role was pure suppression during static siege warfare or naval combat. If placed in a heavily fortified tower overlooking a narrow breach in a city wall, the Polybolos could unleash an uninterrupted stream of bolts into that specific choke point, making it physically impossible for enemy soldiers to enter the gap. On a war galley, it could be used to sweep the deck of an enemy ship before a boarding action, keeping the hostile crew pinned down behind their wooden shields. The psychological impact of facing this machine cannot be overstated. For ancient warriors accustomed to the predictable rhythm of volley fire, where they could count the seconds between incoming projectiles to advance safely, the Polybolos shattered the fundamental rules of engagement. It delivered a relentless, unbroken cadence of death. Yet, despite its terrifying potential, the military establishment eventually sidelined the repeating catapult. The Roman military system, characteristically systematic and pragmatic, calculated that the immense maintenance costs, the highly complex repair procedures, and the absolute necessity for perfectly machined ammunition outweighed the tactical benefits of rapid fire. They opted for a doctrine of overwhelming volume through sheer numbers, preferring to field hundreds of highly reliable, single-shot ballistae rather than a handful of delicate, temperamental machine guns. The story of the Polybolos is a profound testament to the ingenuity of the ancient mind. It proves that the desire to automate violence and remove the human limitation of fatigue from warfare is not a modern phenomenon at all. The blueprint for industrial slaughter existed over 2,000 years ago, constrained only by the limits of ancient woodworking and iron forging. Looking at the brilliant flat-link chains and cam-operated magazines of Dionysius's invention, we are forced to confront a striking historical reality. Technology rarely wins wars on its own. If the Hellenistic kingdoms had possessed the industrial infrastructure to mass-produce perfectly standardized ammunition, would the battlefields of antiquity have resembled the trenches of the modern era? Or is the nature of war ultimately dictated by the limits of the supply chain?